Off Qatar's coast, engineers imagined a transportation link beneath an unforgiving sea. Below the surface, soft sediment concealed the first obstacle to construction.
This engineering concept imagines Qatar's $45 billion tunnel from survey to...
The proposed route would stretch nearly 40 miles between strategic transport hubs.
2 parallel tubes would carry high-speed rail and automotive traffic underwater. At depth, the surrounding water would impose immense pressure on every joint.
Surface construction would also face violent storms, cross-currents, and extreme wave loading.
Engineers first tested whether the Honeycomb shell could redistribute deep-sea loads.
A microscopic alignment error could transform a small leak into catastrophic flooding.
With the concept approved, the first offshore survey mission could finally begin.
Existing surface logistics depended on congested terminals, ferries, and variable marine schedules.
Weather and shipping traffic made conventional ferry travel slower and less predictable.
A permanent underwater link promised steadier freight movement across the region.
Forecasts showed future demand exceeding the capacity of existing transportation systems.
Liam identified the central problem: weak seabed soils beneath precision structural joints.
Every discipline had to solve different problems without breaking one shared geometry. The cross-section combined transport, drainage, maintenance, and emergency systems in one structure. The proposed budget reflected extraordinary material volumes and specialized marine equipment.
The challenge was manufacturing giant sections, then joining them underwater with laboratory precision.
The national ambition now became a physical construction campaign on the coast. Multi-beam sonar mapped ridges, depressions, buried channels, and soft seabed deposits. Laser scanning and GNSS established the project's first precision coordinate network. ROVs inspected how bottom currents disturbed sediment around fixed reference markers.
Core samples revealed mud, clay, sand, and weak carbonate layers below.
Laboratory testing measured density, shear strength, compressibility, and moisture content. Untreated seabed allowed the massive section to settle unevenly under simulated load. The foundation changed to dredged trenches, granular bedding, and controlled leveling.
Zhang transferred surface positioning into the subsea installation zone using acoustic references.
David calibrated pressure and alignment sensors before underwater qualification testing began.
High-pressure jets tested whether prototype gaskets could maintain reliable sealing geometry.
Emma rejected one seal after detecting a microscopic defect outside tolerance.
Concrete testing verified strength and low permeability for long-term subsea exposure.
The Honeycomb matrix redistributed concentrated force across thousands of connected structural cells. Full-scale shell sections were scanned immediately after precision molding. A pressurized chamber recreated deep water loads around a full structural joint. Pressure climbed in stages while the prototype joint remained completely dry. An abnormal spike proved automated safety shutdown had to react immediately. Redundant sensing and automatic isolation were added to the control architecture.
Engineers modeled how extreme waves could alter pressure during exposed installation stages.
Storm trials measured vessel motion, current direction, wave height, and positioning drift.
Conventional crane positioning could not hold millimeter alignment in changing crosscurrents. The solution combined dynamic positioning, AI ballast control, lasers, and ROV inspection, computer-controlled ballast-adjusted prototype attitude by fractions of a degree. ROV pilots guided the prototype toward fixed underwater alignment targets.
Vacuum pressure pulled the joint closed, while sensors confirmed even gasket compression.
Repeated pressure cycles produced no measurable leakage, clearing the joining method. The design teams finalized every structural, transport, service, and sealing interface. Fabrication halls rose large enough to handle unprecedented tunnel section mass. Specialized equipment arrived as the coastal precast complex moved toward production. Engineering theory was finally becoming a full-scale 20,000-ton structure. Thousands of reinforcing bars formed the skeleton of each enormous tunnel section. Automated bending lines maintained repeatable geometry before modules entered the casting hall. Jacks stopped casting until mold supports returned to the specified dimensional tolerance. High-performance concrete was batched under tightly controlled material and temperature conditions. Multiple pumps placed concrete while vibration removed trapped air around critical reinforcement. Embedded sensors tracked curing temperatures through the segment's massive concrete walls.
After curing, scanners searched the exposed concrete for dimensional deviation.
Reinforced honeycomb panels were positioned along designated structural and viewing zones. Structural connectors were tightened in sequence to avoid distorting the shell geometry.
EMA verified coatings, composite joints, embedded seals, and precision contact surfaces.
Aerospace-grade gaskets were installed only after precision surfaces passed contamination checks. Temporary ballast and monitoring systems prepared the segment for controlled marine transport. Controlled flooding gradually made the 20,000-ton segment buoyant inside the basin.
Tugboats carefully pulled the floating segment from the basin toward open water.
From above, the tugboats revealed the extraordinary scale of each floating section. Cole removed unstable sediment to create the engineered trench beneath the root.
Suction dredgers shaped the trench while Sonar continuously verified depth and profile.
Engineered bedding replaced weak sediment and created a controlled receiving surface. ROV lasers confirmed the bedding remained within the permitted elevation tolerance.
Controlled ballast flooding began the segment's slow descent below the surface.
Liam monitored every movement, while ballast and positioning systems controlled the descent.
ROV cameras tracked the giant section approaching its prepared seabed foundation.
AI ballast corrections brought the section within centimeters of its target.
The first permanent joint passed its dry pressure test without measurable leakage.
Months later, repeated installation had extended the tunnel far beneath the Gulf. Weather radar suddenly showed an electrical storm intensifying faster than forecast.
Postponement carried its own risk because the partially submerged segment remained exposed.
Liam authorized restricted operations with extra tugboats and emergency power standing by.
Rain intensified as the critical segment descended into increasingly unstable conditions.
A rogue wave approached while deck crews rushed to secure exposed equipment.
Dynamic positioning thrusters surged to prevent the crane barges from drifting off station.
Below, turbulent currents transferred changing loads into the suspended section.
We have conflicting ballast readings. Zone 4C is compromised.
Liam halted descent while technicians compared pressure, trim, and pump flow data. A nearby lightning strike disrupted the primary ballast control communications network.
One ballast valve bank remained open after communication failed.
Extra seawater entered one side, accelerating the segment beyond its planned descent.
ROV footage confirmed a dangerous tilt developing toward the deeper trench edge.
The primary pump network failed to acknowledge Liam's emergency stop command.
Ryan cleared exposed decks as conditions exceeded normal personnel safety limits.
Pressure data proved the structure was intact. Ballast imbalance caused the descent.
Cole reached auxiliary control, while backup generators struggled to synchronize. Clearance disappeared rapidly as one guide cable approached its maximum load. Lightning exposed the tilted section as alarms intensified across the fleet. Liam bypassed the failing network and uploaded the reverse ballast protocol locally. Backup synchronization began with only seconds of seabed clearance remaining. At 3 seconds, the segment passed dangerously close to foundation equipment. At 1 second, stable voltage finally activated the reverse ballast pumps. The section stopped only feet above the trench, avoiding catastrophic impact. Post-storm analysis revealed inadequate isolation between primary and local ballast controllers. The team reconstructed every command and structural movement second by second.
Redundant sensors distinguished ballast instability from actual structural leakage during the emergency.
Cole's findings showed backup pumps needed continuously available local power. Each segment gained independent battery-supported ballast control for communication loss emergencies. Predictive software now corrected instability before movement exceeded safe operating limits. Ryan introduced stricter storm thresholds, requiring earlier suspension of offshore installation.
Upgraded controls were installed while ROVs inspected the storm-stressed structure.
Subsea laser scans confirmed the recovered section remained dimensionally intact. Heavy lift barges and corrected ballast restored the section's proper attitude. 3 independent alignment systems agreed before the second descent was authorized. ROV thrusters cleared sediment and exposed the precision foundation markers again. The upgraded ballast system held pitch and roll nearly level during approach. Hydraulic guide keys mechanically centered the section as laser targets converged. Vacuum pressure pulled both 20,000-ton structures into uniform gasket contact. Emma verified the dry joint through staged external pressure testing. With no leakage, crews locked, grouted, and instrumented the permanent connection. The upgraded control system was retrofitted across every active installation unit. With safeguards upgraded, subsea installation resumed across multiple coordinated workfronts. Sonar revealed another weak zone, requiring additional trench excavation before installation.
Instrumented foundation material replaced weak soil and tracked future long-term settlement.
Jack increased scanning frequency before every completed segment left the factory.
Emma cleared the final major segment after its seal verification passed.
The final segment descended and closed the last gap in the route. Stable vacuum pressure confirmed the continuous structural corridor was finally complete.
Temporary marine systems gave way to permanent drainage, ventilation, lighting, and monitoring.
Rail crews installed the magnetic guideway under continuous automated alignment control.
Electrical crews connected power, communications, emergency lighting, and structural monitoring networks.
Roadway crews completed pavement, drainage, barriers, lighting, and emergency guidance systems.
Central passages connected transport tubes with maintenance spaces and emergency refuge areas.
A full evacuation drill tested fire doors, refuge routes, and passenger movement. Ryan's final walkthrough verified communications, ventilation, fire suppression, and backup power.
Emma compared final moisture readings against every segment's original dry baseline.
External ROVs inspected coatings, supports, structural transitions, and monitoring housings.
Hydraulic loading confirmed the representative structure remained stable and completely dry.
The magnetic guideway energized, lifting the stationary train fractionally above its supports. The first moving test measured guideway alignment, vibration, power stability, and response. Each faster run tested train aerodynamics, power, emergency systems, and tunnel response. The magnetic test train finally exceeded 250 miles per hour. Autonomous roadway tests verified spacing, lighting, detection, and traffic control logic.
Another severe storm provided a full-scale operational test against changing marine loads.
Deep below the storm, passengers experienced a calm and stable ride.
Protected viewing sections revealed marine life beyond the pressure-resistant honeycomb structure.
A digital twin unified every structural and operational system into one network.
Tunnel traffic continued even when severe weather disrupted conventional marine transport.
The concept had progressed from unstable seabed surveys to an operating transport artery.
The completed tunnel represented thousands of coordinated engineering decisions across every discipline. Qatar's ambition combined international construction expertise with advanced American-engineered control systems.
Above, the Gulf remained violent. Below, the engineered structure remained controlled.
When precision meets impossible conditions, even the sea can become a road.